So we're looking at problem 50 here. You can see there are 3 equal positive charges, 1, 2, and 3. And you can see that they're all corners of an equilateral triangle of side A. They all have A between them. And they ask us to draw what the electric field looks like. So first I'm going to actually repeat the diagram down here. So I'm going to draw plus here. I'm going to draw plus there. And I'm going to draw plus there. And again, we're supposing those are A apart. And I know that there won't be any lines between the charges. Why? Because there can't be an electric field line between them. Think about what would happen to a positive test charge if I put it there. It would be repelled by the one, but it would be repelled by the other. So it couldn't possibly follow that whole line out. Any line that went toward this would end up going away. Same with one here, it would go away. Okay. The same would happen for all of these. If it went out like this, it would go away. Sorry, I didn't draw that well. Same here, this one would go away. Same here, a line here would go away, and a line there would also go away. Now the ones on the opposite side, like that are like maybe that are kind of in between those ones will go straight out, straight out, straight out, and all the ones in between would sort of curve away. Okay. Now there's not a right number, but I do know that I drew 5 on this one, so I'm going to draw the exact same number on this one as well. And it's going to repel, but not as much from that one. And same here. Okay. And over here, I'm going to have, again, a slight repulsion along there and a slight repulsion along there. So I'm going to have a diagram that looks something like that. Again, I can't have any lines in the middle. Okay. Okay. That's part A. That's what that looks like. Part B asks, find the location of one point other than 0 where the electric field is 0. Okay. Well, again, it's you know, you can see that there's a big gap in the center where there's no real where there's no electric field lines because there can't be any lines between them. Okay. So you'd guess that in the center would be. And it kind of makes sense if you think about it. Okay. It's going to be an equal distance from all of these charges, okay? And any line, any charge that goes there, that's put there, is going to be pushed equally by all the charges in the direction of the other. So the only place that can have an electric field of 0 would be at the very center, right here. And then you can actually calculate that out. You could find out what the electric field is from the top one. And you could calculate like what the component would be from the bottom one and what the component would be from the bottom one. And again, the electric field here would be down from the top one. The electric field from here would be up because any horizontal component would be counteracted by the one from the right. So you get a component to the left that would cancel out. You get up there, you'd find that those components were equal, and you'd get an electric field of 0 in the center. That'd be the only place they could both be 0. Part C of this problem asks, what's the magnitude and direction, that's part D, of the electric field at P? That's the charge at the top here. Maybe. Okay. Okay. Based on due to the 2 charges at the base. So we have to actually calculate that out. And if we look at that charge, it's going to get from the charge on here, it's going to get an electric field that goes like that. That's the field that comes from the left-hand one. And it's going to have another electric field that goes like that from the right-hand one. Okay. And you can see that they're going to be symmetric, and that the x component of this one is going to be equal to the x component of that one. So we don't even need to figure those out because they're going to exactly be equal in the opposite directions. So the sum of the x components of the electric field is going to be 0. Okay. And because the 2 charges are the same, these 2 charges are equal, and they're the same distance away, okay, the y components are going to be equal. So the sum of the y is going to be 2 times the y from either one of them. And you can see they're all going to make the same angle because it's an equilateral triangle. This angle down here is 45 degrees. So this angle up here has to be 45 degrees. Oh, let me write that on there better. 45 degrees. The angle there has to be 45 degrees also. It's the only way that it can work. So what it means is that to figure this out, I'm going to have to figure out what this is. I'm going to have to take the sine of that. So it's going to be, so my total electric field is going to be 2 times E sub y, which is going to be 2E sine of 45 degrees. Again, they're point charges, so we're going to use K. Q, again, it's just going to be the 1Q. The distance is going to be the distance between them, which is A squared, times the sine of 45, which is going to be, if you put in your calculator, it's going to be root 2 over 2. The 2's will divide out. We'll get an answer of KQ over A squared times root 2. I think in the actual answers I put online, I wrote 1.73 KQ over A squared. But 1.73 is root 2, so you're right there. The direction, you can see from the arrows that we drew, the direction is just going to be up toward the top of the page.